So in the last session we found that if an element is algebraic over a field, then there exists a irreducible polynomial. So this is what we found in the last session. Let E be the extension of F and alpha is an element of E. Then if alpha is algebraic, then there exists an irreducible polynomial P of x in f of x such that P of alpha is equal to 0. And we also mentioned that this is unique only up to a constant factor. For example, if you take Q and R and a polynomial P of x square minus 2, and an element root 2 in R, then the corresponding irreducible polynomial is this. But we also found that this is not the only irreducible polynomial. There can be another one which is a constant multiple of this polynomial. For example, P1 of x 2x square minus 4 or P2 of x 3x square minus 6. These are all irreducible polynomial for which root 2 is a 0. So, but what we want to do is we want to make it as a unique polynomial. For that, what we are going to do is we are going to make the coefficient of the highest degree be 1. So if the highest coefficient of P of x is 1, then we can say that P of x is unique. And such polynomials where the coefficients of the highest degree is 1 is called monic polynomial. So we'll define that unique polynomial here. So let same thing, E be an extension of F and alpha belongs to E be a algebraic element, then there exists a unique monic polynomial, monic irreducible polynomial. P of x such that P of alpha is equal to 0. Now I am talking only about x square minus 2. I don't consider these because these are not monic polynomial. So there exists only one monic irreducible polynomial for which alpha can be a 0. And this polynomial is called the irreducible polynomial irreducible polynomial for alpha over f. And is denoted by irreducible on alpha comma f, and its degree is denoted by degree of alpha over f. So we'll take an example. We already took one and we'll take a couple more. Let us assume that example. Let's assume that f is equal to q and E is equal to C, and alpha is equal to square root of 1 plus cube root of 2. Let us see whether this is an algebraic element, and we'll try to find out the irreducible polynomial and also the degree. So how do you find out? What we need to do is we need to find out a polynomial in f of x such that this could be a 0. In order to do that, you remove all the radicals, the roots, cube roots and all stuff. So square is equal to 1 plus cube root of 2. That implies alpha square minus 1 is equal to cube root of 2. That implies alpha cube minus 1 whole cube equal to 2. So this is square. And that implies alpha square minus 1 whole cube minus 2 is equal to 0. So the polynomial, the irreducible polynomial of alpha, that is square root of 1 plus cube root of 2 comma q, is equal to, it is the polynomial, so it will be x square minus 1 whole cube minus 2. You can expand this, I'm not going to do it right now, but evidently this is a monic polynomial and this is an irreducible polynomial. We'll do a couple more examples. We'll do another example here. Again, f is equal to q and E is equal to C, and alpha, I'm going to take it as square root of cube root of 2 minus I. This is definitely an element of C. So again, remove all these square roots and cube roots. So what we'll have is alpha square is equal to cube root of 2 minus I. And that means alpha square minus 1 is equal to cube root of 2. So if you take this minus I, if you take the cubes, so alpha cube minus I whole cube equal to 2, or minus 2 equal to Okay, equal to 2. So if you expand this, that will be alpha to the power of 9 minus 3 alpha to the power of 6 I plus 3 alpha cube oh no, this is square, right? This is square, so this will be alpha to the power of 6 minus 3 alpha to the power of 4I plus 3 alpha square I square minus I cube equal to 2. So this is alpha to the power of 6 minus 3 alpha 4 I minus 3 alpha square plus I is equal to 2. So alpha to the power of 6 minus 3 alpha square minus 2 equal to 3 alpha to the power of 4 minus I minus 1 of I. What you do is again squaring alpha to the power of 6 minus 3 alpha square minus 2 whole square is equal to minus 3 alpha to the power of minus 1 whole square. So this will be plus equal to 0. So this is our irreducible polynomial. This is actually the irreducible polynomial over Q, and of course the degree is going to be 12. Definitely this is going to be a monic polynomial, and it's an irreducible polynomial too. So we'll come back to the same example. Root 2 belongs to R, and R is an extension of Q. And we know that there is a polynomial x square minus 2 belongs to Q of x such that root 2 is a 0 of that polynomial. And we also know that we can find an extension of Q such that contains a 0 of a given polynomial. See, here, you know, R is an extension, definitely it is very clear. But our problem, what we are going to do is, we are going to find out, is there any smaller extension of Q containing R? R is a big number. It's a big ring. It's a huge extension. We don't want that. We want to have the smallest extension of Q containing an element from this extension. See, if you that means if Q union root 2 would have been a field, that is exactly what we are looking for. But unfortunately, it is not that easy, because Q union root 2 is a superset of Q, but it's not a field. It is not closed even under addition. So we want to find out the smallest extension of Q containing this root 2. And it doesn't need to be an algebraic. This is root 2 is an algebraic. We want to find out if there is an extension like for a transcendental number R and Q over R such that pi is included in the extension of the smallest extension of Q. So that is our objective. The smallest extension of a field containing an element outside that field. So let us start with this the definition again. Let E be an extension of F and alpha belongs to E. So we have two cases here. Case 1 is alpha is algebraic. Or F. Alpha is algebraic over F means there is an irreducible monic polynomial over F. So let P of x is equal to the irreducible polynomial of alpha over F. This is actually a monic irreducible polynomial because alpha is algebraic. If it's transcendental, this is not the case. We are going to handle it differently. And well, let us define the evaluation map at alpha. Evaluation map always goes from the ring of polynomials over F to E. What is the meaning of this? This means P of alpha is equal to 0. So we are trying to find out the image of phi alpha. So what you do is you take an element from here. Let f of x belongs to f of x. Then see what is the image of this f of x. See, f of x and p of x are both in f of x. So that means there exist two elements in f of x such that f of x is equal to p of x times q of x plus r of x, where degree of r of x is less than degree of p of x. So let us see what is happening here. Phi alpha of f of x is equal to, by definition, it is actually f of alpha. And that is actually equal to p of alpha times q of alpha plus r of alpha. But this is 0 because this is the irreducible polynomial, monic irreducible polynomial for which alpha is a 0. So this is actually equal to r of alpha. So what is happening here? The image of any polynomial under this map is the remainder polynomial at alpha when this polynomial is divided by the irreducible polynomial. So actually we can write it like this. This is equal to R of alpha mod P of x. And what is this? This actually belongs to the principal ideal generated by P of x. So basically what we are going to arrive at is phi of alpha of f of x is equal to R of alpha plus this. So it will be, it's actually isomorphic to, probably it's isomorphic to f of x P of x, because this is actually the ideal generated by P of x multiplied by any other element of f of x. Then whatever is the remaining, that is going to be the image of this. So you see, what are the elements of this? The elements of f of x over P of x is P of x plus some function, and the degree of this is less than the degree of P of x. So that is exactly what is happening here. So, and P of x is an irreducible polynomial. So this is actually a field containing the 0 of P of x. This contains, see, we already established that this is an extension of f of x containing the 0 of P of x. So we can say f of x over the ideal generated by P of x is the smallest field containing alpha and f. F is because by the evaluation definition itself, you can see that f is embedded here, because any element from f, any element a from f, we can consider that as an element like this, a plus P of x. So this is actually equal to f. This is actually equal to a. So every element of f is identified like this. This is, and it contains alpha, because alpha is a 0 of P of x. Why is it the smallest one? Because if you take any other smaller field than this, then this will not become a field. Let us assume that, see, alpha is a root of P of x. And if you take irreducible polynomial, alpha is a 0 of the irreducible polynomial here. If you want to make this as a smaller one, then we need to take the multiples of this, otherwise it will not be smaller, it will be bigger. So if you want to take if you take another multiple of this, let's say if you take f of, or let's say h of x is equal to h1 of x times p of x, and if you take this one, this is actually smaller than this, and this also contains a alpha, but the problem is this is not a field, because this is not an irreducible polynomial. It is field only if this is an irreducible polynomial. So this is not possible. So the smallest field containing alpha and f is going to be this. So if alpha is algebraic, we have a smallest field containing alpha and f. Let us assume that alpha is transcendental. Let alpha belongs to E be transcendental. What does that mean? That means that phi alpha, the evaluation map at alpha from f of x to E is 1, 1. Right? We already established this result. What is f of x? F of x is not a field, but it is an integral domain. F of x is not a field, but it is an integral domain because f is a field. F is a field, so this is an integral domain, meaning that if you take two elements from here, multiply is equal to 0, one of them has to be 0. So that means, and it is a 1, 1 map. So that means phi of alpha of f of x is an integral domain. Containing alpha and f. Why alpha and f? Because if you take phi of alpha of x, that is alpha, and phi of alpha of a is equal to a for all a in f. So this actually contains alpha and f, but still we are not there because this is only an integral domain. But we already know that if you have an integral domain, we can construct an extension field. It's called a field of quotients. So this integral domain will denote by, let this integral domain be denoted by f square bracket alpha. So this is an integral domain, so then the field of quotient of f of alpha is the smallest field containing alpha and f. So in both the cases it is denoted by this smallest field. This field is denoted by f parenthesis alpha, not square bracket, parenthesis. So here also I will say and is denoted by f of alpha. Integral domain is square bracket and the field is the parenthesis, curly brackets. What are the elements of this f of alpha? By the way, when it is transcendental, f of alpha will be a polynomial over alpha, like p of alpha by q of alpha. It's a field of quotients. So you represent an element in alpha by a quotient of two elements from the integral domain. So in either way, we found that there is a smallest field containing alpha and f. So what we found is, let E be an extension of f and alpha belongs to E, then there exists a field as the smallest field containing alpha and f. Then the smallest field containing alpha and f is called simple extension of alpha. Over f, and is denoted by f of alpha. And if alpha is algebraic, simple extension of alpha over f is isomorphic to what? Isomorphic to f of x over the ideal generated by the irreducible polynomial of alpha over f. If alpha is transcendental, every element of f of alpha is a quotient of polynomials in alpha over f. Okay? Now we are going to find out some result when it is algebraic. Let's see what happens. So let alpha be algebraic. So what is happening here? It is actually isomorphic to this. So we'll take the evaluation map. Let alpha, phi alpha be the evaluation map. Be the evaluation map. So we already found that for f of x in f of x phi alpha of f of x is equal to r of alpha, where r of x is the remainder polynomial when f of x is divided by p of x. That means if f of x equal to q of p of x times q of x plus r of x, then phi of alpha of f of x is equal to alpha. And what else we know about the simple extension? The simple extension f of alpha is actually the image of, what is the image of this? The image of this one is the field, the quotient field f of x over irreducible polynomial of f over alpha over f. So the image of this, so image of this is actually f of alpha is equal to image of phi of alpha of f of x. And what are they? They are r of x, r of alpha such that f of x is equal to q of x times p of x plus r of x. And what is other condition here? Degree of r of x is less than degree, strictly less than degree of p of x. So the elements of the simple extension when alpha is an algebraic is this: f alpha is equal to a polynomial in alpha whose degree is less than the degree of the irreducible polynomial over f for which alpha is a 0. So alpha, see, this will be equal to let's say b0 plus b1 alpha plus b2 alpha square plus dash dash b n minus 1 alpha n minus 1 bi's in f, and n is equal to the degree of alpha over f, which means that it is the degree of the irreducible polynomial for alpha over f. So any simple extension of an algebraic number is of this form. For example, I will write an example also before we conclude this session. Let us say take q, f is equal to q, and e is equal to r, and alpha alpha is equal to root 2. Then q of root 2 is equal to, what is the monic polynomial, that is irreducible monic polynomial. So irreducible monic polynomial of root 2 over q is equal to x square minus 2. So that is actually equal to, if you write it like this, a x square plus 0x minus 2. So this contains all the polynomial in alpha with the degree less than the degree of this polynomial. So this will be where a comma b in f. That is what this says. The simple extension of an algebraic element contains a polynomial in alpha with degree less than the degree of the irreducible polynomial for which that element is a 0.